Okay, so we go back to class. So our final topic related to the buoyant force is the predicting stability of our bodies. Okay, so and for these questions, we have the two parameters are very important. We need to figure out first. So the first one is we call that the centers of the buoyance, and then we call that is the C point. And the second in here, the G, we call that is the center of gravity. Okay, the G is the center of the gravity. Okay, so based on this, the 2 points showing here, C and G, the relatively positions, we can predict the body is stable or not. And sometimes we have the two conditions. The first one is immersed, and the second one is floating. We only have the two conditions, and we are trying to predict the stability of the bodies. As the showing here, the first one, you can see the C is the buoyant force. So we have the upward force. And the gravity, G, we have the downward force, W. If the upward force and the downward force, they are parallels along the single lines, that means our body didn't rotate, right? Because there is no any moment. But if we see the right conditions, we have the G going down again, and then we have the buoyant force going up. But the two forces, they don't locate at the single lines. So it should have some moment. Okay, so what kind of moment we have? We will have the clockwise moment. Okay, so you see the button first in here, but we have the clockwise rotate. So the button transfer to here. Okay, so that means if we can figure out the relative position between the C and G, and then we can decide the body will rotate or not. If the body started to rotate, that means the initial condition of the body is unstable. And after the body rotates, maybe will move to the stable conditions. Okay, so the idea is how can we figure out the body's stability problems just based on the C and the G locations. Okay, so this is a true condition, but we focus on the target is the ship. So this is a very famous problems. If we have the ship and we design the ship structures, and how can we determine the ship is stable or non-stable? Okay, so for this problem, I distinguish the ship into the right-hand part and the left-hand part. So the right-hand side in here, and I put the 1 point in here. So in that case, we will have the buoyant force, right? Because the yellow area is immersed into the water or into the liquid. So what is the moment for this problem? By your right hand, and you can do the curls. So you have relative to the center line, you have the length along these directions, and the length factor cross the FB force. You will have the counterclockwise rotate, right? Because this is a length factors. the length factor cross the force factors, we will have the counterclockwise. And then this is the positive moment. This is the positive moment. And then if I go back to see the left hand side in here, so this is our left hand side areas. Again, we still have the upward force related to the buoyant force. But right now the condition is different because the length factors is along these directions. So by use your right hand and you do the cross. So the moment will clockwise rotate, and usually we call that is the negative moment. So we divided the center line into the right hand side and the left hand side. The moment is the opposite. That's why the ship will stable in here. Okay, because the right hand side is the positive moment and left hand side is the negative. But right now we put some disturb. So we disturb the ship. The ship will be disturbed by the ocean wave, right? Not always stand by here. So we have a dispersed by ocean wave. So we'll rotate right, rotate left, rotate right, and repeatedly. So in that case, we disturb the ship. So we have some areas. We have some area inside immersed into the liquid, and some area outside the liquid. Okay, so that's the different conditions because we have more volumes immersed into the liquid. So here we will have some additional buoyant force, right? Because the buoyant force is related to the displaced volumes. So the right hand side we have additional area immersed into the water liquid. So we have additional buoyant force. But the left hand side in here, because this area is uplift from the liquid, so there is no buoyant force, right? So in here we only have the weight, because in that area is uplift to the liquid surface, so it's transferred to the weight contributions. So in that case, what are the moment we have in here? We still have the counterclockwise, the positive moment, but in here we still have the counterclockwise moment. So the shift will rotate back to the center. Because the two sides are positive moments, so the shift will rotate, go back to the center line. OK， 这是很重要的一些小观念，就是说，当我们如果在正中心的时候都不动，其实右边跟左边的 moment 会互相折抵，所以我们的 ship 是不会转动的。可是如果我弹，当然不可能用手指就把船弹动，但是我弹一下船它就动了嘛。那它动了以后，它其实会想要回到中心位置。那它为什么有办法想到回到中心位置？你看我右边这个案例，它的 moment 会是同样都是正的，所以它会转回去中心位置。但是左边这个案例是它本来就已经是稳定的，所以左右的 moment 会互相抵消掉，所以它就会一直想要在中间点。可是你一旦让它有扰动，它就全部都会转成想要让它转回来中心位置的这个 moment。Okay, but normally we call that in the left hand side usually have a negative moment, and the right hand side usually have the positive moments. But if you disturb the ship, the moment will total have the same, always the same positive or always the same negative. Will have a different rotations, but the purpose is the moment would like to put the ship into the center line. Okay. So actually for the stability predictions, we follow the 4th stage. So I write down some sentence in here. Totally, we have the 4th stage. Okay, as the cartoon figure showing here, what is the 1st stage? The 1st stage, we assume we have the alpha angle rotate. So the ship, we have the alpha angle rotate in here. And after the rotate, the C point, what is the C point? The C is the center of the buoyant. The center of the buoyant force. So after you rotate, the center of the buoyant force will move to the C prime. So there is a C prime. So the first step, the center of the buoyant will move to the C prime. Because you have the alpha angle rotate. And then in that moment, we do the vertical line. So I do the vertical line. And when the vertical line cross with the y direction line, and we have the point, we call that the M. The M point is the meta center. The M point, we call that the meta center. 中文叫做定倾中心。定倾中心，就是我要定义它是不是有倾斜的中心。定倾中心 meta center. Okay, and I tell you some ideas how can we predict the stability problems. As you see the GM is not the game manager, right? 我们玩游戏都有 GM 嘛。这是 GM. So what is the GM? GM is the distance, and we call that the GM is the metacentric height. The metacentric height. So I directly tell you the final definitions because the center I write down in here, GM is larger than 0. That means the ship is stable. If the GM smaller 0 than 0, the ship is unstable. So that means how can we compute the distance between the G and M? So it's the distance along this direction, GM. Okay? So this is the idea if I tell you the GM distance smaller than less than 0, that means the body is unstable. Okay? So the purpose, we need to compute the distance between the GM point. Okay? So usually we will compute the CM distance first. So where is the C? The C is in here. So we will first compute the CM distance. So we have the CM distance, right? And then the second, we will compute the CG distance. So where is the CG distance? There is the CG distance. If you calculate the CM minus the CG, final will equal to the GM, right? So usually we will calculate the CM first, and the secondary we compute the CG, and then we can understand how large of the GM. So right now our purpose is how can we compute the CM values? How can we compute the CM value? So the CM is our purpose. But what is the CG? CG is very easy to compute because the C is the buoyant centers and the G is the gravity center. Okay, if your particle body is symmetry, and then you can easily to figure out where is the C and G. Okay, so later we have the exercise. So right now our purpose is how can we compute the CM? Okay, so we go to the next slide. So the first equation showing here is still based on the moment balance. So the left hand side is the total moment. What is the total moment? Because we have the x bar. X bar is the distance between the C and C prime. Between the C and the C prime. And the V is the total volumes. And then this is because we have the gamma. Right hand side, actually we have the gamma V. The gamma, what is the gamma V? The gamma V is the Bouillon force, right? So the V is the displaced volumes. And this is the Bouillon force. If the Bouillon force multiply the x bar, so it is the moment. This is for the left hand side. And the right hand side is the sum of the small displaced volumes. Sum of the small displaced volumes contribute to the moment. Okay? So, but for this equation, because the right hand side we have the gamma, and the left hand side we have the gamma, so we just cancel out both sides gamma. So that means there is a total moment, and the right hand side is we have the I segment. And each segment we have a different moment. Okay, so it depends on the different volumes we have, displaced volume we have, and the small xi distance. Okay, so the next is we write down two sentences. The moment of the V before the heel, and minus. Notice that there is minus the moment of the VAOB. Why the minus? Because the VAOB, where is the VAOB? The VAOB is in here. And as I mentioned, the moment on the left hand side always negative, right? So that's why I use the minus in here. But the right hand side in here is the EOD. The EOD is in here. So the moment contributed to the right hand side, usually we use the positive. Okay, and the next, so the right hand side and the left hand side, the moment before the heel, so there is no any additional moments. So we don't have this item. We only have the second one and the third one. So we do the sum of the AOB and the sum of the EOD moment together. Okay? And as why there is no any negative. The symbol negative disappear when we go to the next step. Because the left hand side AOB is uplift. So I already tell you the weight. There the force will become the weight, not the Bouillon force. Because the AOB area is uplift to the liquid. So not the Bouillon force is the weight. If the weight, the moment will move to counterclockwise. Clockwise, okay? So the moment will be the positive moment. But in the left hand side, if the volume immersed into the liquid, will have the negative moment. So it's a clockwise moment. Okay, will change. So the minus, so there is the positive. Okay, and we do the move to the integrations. So what are the dV? What are the dV for the integrations? So as you can see, the dV is the dA. dA is the in here, and we need to multiply the height and then we can compute the small segment of the volumes. So what is the height? Because we know that is the AX, it is the AX, and the AX, the height in here, along this direction is the height. So we know that the AX, this is the tangent alpha is here. This is the alpha angle. So we know that the tangent alpha is equal to the x over h. So the height is equal to the x tangent alpha. And we have the area, small area dA, multiply the area height in here is equal to the dV. Okay, so that's why we have the dV in equation in here. Okay, so we can just put the dV replaced by the x tangent alpha dA. So this is our final equation. X bar is multiply the total displaced volume is equal to the x squared tangent alpha dA and the x squared tangent alpha dA, but along the different area AOB and the EOD. EOD here is AOB. Okay, and you may figure out in here integrate x squared dA is related to the second moment. Is related to the second moment. So the next slide showing here, we first compute the total. We first compute the total second moment. This is our total second moment. And the tangent alpha is a constant, so we take outside of the integrate. And then please notice that the area in here, we use the water line, the area along the water line. So that means your body cross over with the liquid surface. This is the water line surface. Water line surface. So we know that this item we move to the next. We call that this item can be expanded, follow we have the AOB, EOD, AOEIF, and the BODJH. Okay, so I just depict the AOB first. So this is the AOB and the EOD in here. And what is the AOEIF? This is the AOEIF and the BODJH. BODJH. So we distinguish the four second moment items for the different area. Okay, AOB, EOD, and the AOEIF, and the BODJH. And I directly tell you for the pentagon, and the second moment for the pentagon related to the all axes is always equal to 0. So we can cancel out the final two items. So we know the water line, the second moment along the water line integrate will equal to the AOB and the EOD second moment. Okay, so that's why in here, the square in here, we can directly replace the two items by the second moment along the water line integration. Okay, so finally we can replace, this is the I, the second moment for the total water line area. Okay, so this is our final term. This is our final term. Okay, X bar multiply the total displaced volume is equal to the second moment of the water line area multiply the tangent alpha. Okay, so this is our final. And the next step, we know that what is the x bar. What is the x bar? X bar is in here, and the x bar is equal to the Cn. This the line in blue is the Cn, and we know that the equation is the x bar divided the Cn is equal to the tangent alpha. So we know that the x bar is equal to the Cn tangent alpha. So if you put the Cn tangent go back to this equation, you will have the Cn tangent alpha total volume displaced and the second moment tangent alpha. So we can cancel out both sides of the tangent alpha. And then finally, you know that the Cn is equal to the I divided the displaced volume. As I mentioned before, our purpose is how large length of the Cn distance. So if we can compute the second moment and the displaced volumes of your body, and you can predict the Cn distance. Okay, if we know the Cn distance, and we can compute the Cg distance, and the Cn minus Cg, we will have the metacentric height. And I tell you the metacentric height smaller than 0 is unstable, right? And the larger than 0 is stable. So we just based on the Gn values to predict the body is stable or not. So the key knowledge in here, we should compute the Cn distance first, and then we can find out the Cn distance, and the two number minus result, we will have the Gn. OK， 所以我刚才的过程其实如果你听不太懂没有关系，但是我们的关键是要算出 Cn， 就是定倾中心跟我的浮力中心的距离。如果我算得出来，我只要再去算 Cg 等于多少，两个东西相扣就可以去知道 Gn 是大于0还小于0。如果 Gn 大于0，就代表现在这个状态是稳定的。Gn 小于0，就代表这个状态是不稳定的。那所以关键点是 Cn 怎么算 ？Cn 跟二次举张量，二次举的这个恶性惯性举跟你的物体下沉在液体中的体积有多少？哦，不是整个物体的体积哦，是它在液体里面的占有的体积有多少 ？OK。So we may have the exercise, and today we only have the 2 exercises, and then we finish the class. So the exercise is just a practice to how can we predict the stability problem. So we put the wood, and the length of the wood is the 60 centimeters, and the weight of the wood is the 318 Newton. So we just write down some important information. The weight of the wood is 318 Newtons. And you see our final answer, the block is not stable. Okay, so we can figure out the Gn should be smaller than 0, right? Because unstable. And we consider the condition is rotated axis is along the longitude. That means this direction is our rotated axis. And the width is 30 centimeter and 30 centimeter high. So this is the width, and this is the height. Okay, so and this is the length. The 60 centimeter is the long along the longitude directions. Okay, so first we didn't know the H, right? Because the wood just floating on the liquid surface. But we didn't know how large the H in here. But the H is quite important because we need to calculate the VD, right? We need to calculate the VD. The D is the displaced air volumes. So we need to know the height immersed into the water. Okay, so it's our first unknown parameters. So what is the VD? So we know that for this question, the wood already floating on the liquid surface. So we have the force balance is the buoyant force, okay, should be equal to the weight, right? That's why the wood floating on liquid surface. Then the liquid what we use in here is the water, okay? So FB will equal to the gamma water and the displaced volumes, and will equal to the weight. The weight is the W in here. So we know actually the FD will equal to the W divided the gamma W. Okay, so the W is the 318 Newton divided the gamma W is the 9A110 Newton divided the cubic meter. Okay, so the volume, we can compute the volume very easy. It's equal to the 0.0324 cubic meter. Okay, and then how can we compute the displaced volumes? By another way, because we didn't know the height in here, okay, but we know that if we have the height and then multiply the width, the 30 centimeter is equal to the 0.3 meters, and we know that the long is the 60 centimeters. So we know that is 0.6. So actually it is 0.18 H is our volume, right? Displaced volume. So we can make the balance is the 0.18 H is equal to 0.0324, and the H will equal to 0.0324 divided 0.18. Okay, so the H is equal to 0.18 meters and equal to 18 centimeters. Okay, so right now we have the H. Okay, and then why I would like to compute the H? Because I would like to determine the C and the G. Where is our G and C? Because if I can compute the C and G, I can calculate the CG distance, right? So the C, we know that the H is the 18 centimeter, and the C is the buoyant centers. So that the black dot in here, the distance between the C, this is our C point, to the bottom is 9 centimeter, right? Because of the half of the H. Okay, and where is the G? The G, because the total length is 30 centimeters, so the G should be higher than the C point. This is the G, and the G, the distance to the bottom in here is the 15 centimeter. Okay, so we have the C and G, the locations. So we actually know the CG distance. what is the CG distance? The CG distance should be equal to the 15 centimeters minus the 9 centimeters. So it's equal to the 6 centimeters. This is our CG distance, right? Okay, and then equal to 0.06 meters. Okay, so that's why I tell you the C and G is no problem, because our body always the symmetry. So it is free to find out the C and the G point. So our key knowledge in here is how can we predict the Cn distance, right? As I mentioned, the Cn is equal to, if you forgot, but the previous slide tell you the Cn in here is equal to the second moment divided the displaced volumes. So we follow these equations. It's equal to the I divided the Vd, right? The D is the displaced volume. So what is the I in here? Because the I is the cross-section area of the water line. So in here, what is the cross-section area? Is in here, right? This is the cross-section area along the water line. So the area should be like this shape. This is our water surface. Okay? And along these directions is the longitude directions. So the length of this direction is 0.6 meter. And this is our rotated axis. Okay, this is our rotate, because our answer is longitude is our rotated axis. So this is a right angle shape. So the moment for this question is 12 over 6, 0.6. Because the longitude length is our rotated axis. So I use the 1 power for the 0.6 and the 3 power for the 0.3. The 0.3 is the width. It is the width. It's a 0.3 meters. Okay, it is a width. Okay, so we can compute the second moment for these questions. Okay, by my calculators. And the 12. So it's around the 1.35 10 minus 3 4 powers meters. And we already know the FD. The FD we already compute in here. So we can put the number inside. So we know that the Cm is equal to 1.35 10 minus 3 meter 4 powers divided the 0.0324 meter cubic. So you can compute the length for a Cn is around the 0.0416 meter. So it is equal to the 4.17 centimeter. Okay, so right now you can compute the Gn, the length, because the Gn length is equal to the Cn minus the Cg length. So I use the centimeter unit. So the Cm is the 4.17 centimeter minus the Cg is the 6 centimeter. Okay. So it will the minus 1.83 smaller than 0. So we conclude that the block is not stable along the longitude axis. Okay? So the key knowledge is you need to determine the Gn is larger than 0 or not. And then you can predict the stability problems. Okay? So when the block rotates, because unstable, so the block will rotate. So the second question is the following questions. After the block rotate and under these conditions, and you need to answer the question again, is it stable or not? Because the block rotate. So right now we need to predict the second questions. And the answer showing here, the block will be stable in this position. Okay, so you need to recalculate the problems. So for this problem, we already know the width in here is the W. Okay, so this is the surface water line, and we know the height is the half of the W. So it is the height, half of the W width. Okay, and the question is very nice because we already know this point is the G. Okay, and this point is the C. And the question already tell you the CG distance is the 5.73 centimeters. So we only need to calculate the CN length, right? And the CN length is the I divided the VD again. So we need to know the problem for this the questions, what are the VD distance the VD, and then what is the W. If we know the W, so we can compute all of the solutions. Okay, so how can we compute the VD? The VD, again, the VD, the buoyant force, the gamma WVD will also equal to the weight again, right? So we don't need to recalculate the VD because we already know the VD on previous questions with VD is 0.0324. So this is 0.0324 meter cubic. But right now, we don't know the W length. So, but we know the VD, right? The VD is the area volume in here. This is the VD. This is the VD. So, we know that the VD will equal to the total volumes. What are the total volumes? The total volume is the 0.3 multiplied the 0.3 multiplied the 0.6, right? The width and the height and the long. And this is the total volumes. Should be minus the triangular shape in here. So minus the W multiplied the half of the W is the bottom length multiplied the height of the triangle, and divided the two, and multiply the length along the longitude. Okay, so you can compute. This is 0.3 multiplied 0.3 multiplied 0.6. So the first item is 0.054 minus the 0.6 divided the 4. So this is a 0.1 W squared. So you can put the number, try to calculate the W. So the VD is equal to 0.0324 equal to 0.054 minus 0.15 W squared. So the W squared will equal to wait for a moment. So it's equal to the 0.144, and then we use the root. It's equal to 0.38 around the 0.38 meter. Okay, so since we have the W, okay, so we can compute the I The I is again, because the cross-section surface area in here, the rotated axis is still along the longitude. Okay, so we have 12. We have 12, and the longitude length is 0.6. But right now the width is different. The width is 0.38 cubit. So we can compute the number for these questions. Okay, and multiply 0.6 divided by 12. So this is around 2.74 10 minus 3 powers, the meter 4 powers. And so you can directly compute the Cn very quickly because the 2.74 10 minus 3 powers divided the FD is 0.0324. Okay, so you can predict the length is equal to 0.0847 meters and equal to the 8.47 centimeter. So the Gn will equal to the Cn minus the Cg. Okay, so the number for these questions, the Gn is equal to 2.734. So the larger than 0. So at this stage, the block will be stable. Okay, so the key knowledge, you just decided what's your problems and decided the C and G point. So you can calculate the CG distance very quickly. And then the Cm distance you should base on the equation showing here. It's a very important equation showing here. Okay, and then you need to know how to calculate the second moment based on your shape, the water line shape. Okay, so that's all. So we finished the chapter 3, and this is our final topic, the buoyant force and the prediction the stability problems.